Hello, ladies and gentlemen. This is going to be the very first, I guess, the first high quality video that you guys are actually going to see. Also realize that it's going to be very long because in this one I cover about, I want to say 90% of all of the material that we need to for the entire first unit. So, when you're watching this video, you might want to chunk it up into bits so you don't go brain dead midway through, and that's totally fine. That's the whole reason why we're doing this. So if you want to watch the first third of it, take a break, watch the next third during another lesson, and watch the final third again, that's totally fine. So what we're going to be talking about is moles and stoichiometric relationships. I believe you guys started to see the mole at the end of 10th grade and this idea, so some of this should be review, I hope, but if not, that's totally fine. These are the things that we're going to try to really hammer home in this one. So I'm not going to spend a whole lot of time on this. This is just the game plan of how we're going to approach this. So first off, what is a mole? We measure mass in grams and we measure volume in cubic meters, and then this could change, so you might end up seeing decimeters, cubed, cubic, centimeters, anything like this, but most of the time we're going to have to convert it back to cubic meters, and then we'll go over that as well. That's all part of the IB DP program. And then lastly, we count particles, atoms, and molecules in moles. So it's what a mole is it's really just kind of like a dozen. I'm going to get to that in a bit. So if we have a carbon-12 atom, which means it's going to have 6 protons and then 6 neutrons, that means it's going to have an atomic mass unit of 12, so it's going to weigh 12. 1 mole of carbon atoms is going to weigh 12 grams. So, and I'm going to bring this up a few different times. So 1 mole is actually going to be equal to the atomic mass in grams. The mole is also a specific number, and we're going to come to that very soon here. I'm going to go through this pretty quick because this first half is pretty repetitive. It happens over and over and over again. So I want you to see that relationship. 12 AMUs is the same. It's going to give you a clue that you're going to be using 12 grams. Avogadro's number is the number that a mole is. So like we said before, 1 mole is equal to the atomic mass in grams. But Avogadro's number is also what a mole is. So 1 mole is equal to this number. So it's also 1 mole is equal to 6.02 times 10 to the 23rd. So a mole can be 2 different things, and it's a way for us to go between atoms, which we can't really count out, to grams, which we can measure out. It's a good way, it's a vehicle for us to go from one thing to another, something on the micro level that we can't even see at the sub-micro level, atoms, to on the macro level, grams, something we can measure, a tangible thing. So it's also going to be a counting unit. It's always this number. It's Avogadro's number is always this. It's the same idea as a dozen is always 12. So if we have a mole of cats, we have 6.02 times 10 to the 23rd cats. If we have 2.4 moles of cats, then we're just going to multiply Avogadro's number by that much. So 2 by 2.4. This is the answer, so it would really just be 2.40 times, and then that number, 6.02 times 10 to the 23rd. And then you would end up with, when you put it in your calculator, it would spit it out like this. But since we're doing this in proper scientific notation, you need to move this decimal place over and then readjust your exponent. So the correct answer would be 1.44 times 10 to the 24th. I don't know the last time you've seen scientific notation, so I'm working with the assumption that you've seen it before. I'm sure you have. And I'm kind of working with the assumption that you know it. If you don't, talk to me. Always, always talk to me. Say, I don't remember how to do this, and then we'll go over it again pretty quickly. I already talked about this. I hit on it earlier. So the atomic mass in grams, this equals the mass of 1 mole of an element. And you can find this on the periodic table. So if you're looking at, excuse me, if you're looking at your little, I'm going to just quick draw in a carbon box from the periodic table box for carbon. Remember, the top one is the atomic number. You aren't going to use that number. Instead, what you're going to be using is this one, this 12.02, and that's the atomic mass. And there you can see it right there. 12.01 grams of carbon has the same number of atoms as this many grams of hydrogen. And it has the same number of atoms as this many grams of iron. This is just because one individual atom of iron, so iron weighs more per atom. It's the same idea as if I had a dozen feathers. Feathers are very light, they're not going to weigh much, as compared to a dozen, ooh, dropped my pen, as compared to a dozen liters of milk. A liter is going to weigh more. They're going to be the same number. I'll have 12 feathers, 12 liters of milk, but the liters of milk are going to weigh more because individually they weigh more. So when we set up our relation, we just say 12.01 grams is equal to 1 mole of carbon, and then remember this is also equal to 6.02 times 10 to the 23rd atoms of carbon. Very key idea. So we count things out by weighing them. Since we can't count out the individual atoms, we weigh them and we know based on this relationship how many atoms there actually are. This is me just hammering it home over and over. So moles of atoms is equal to the atomic mass in grams. So if I'm looking at aluminum, it's going to be 26.92 grams is equal to 1 mole. If it's gold, since gold weighs more, each atom weighs more, it's going to be 196.97, 107.87 for the mole of silver, and boron's a lighter atom, so it's going to weigh more. Or way less, sorry. These are all from the periodic table. Ugh, running out of room, sorry. Those are all just from the periodic table. I looked at the periodic table, saw the bottom number, and then I knew that's what they were. So, real quick review, how many atoms are there in a mole? 6.02 times 10 to the 23 atoms. It doesn't matter what the element is. And then if we have a mole of hydrogen, is it going to have the same number as a mole of helium? Yes. But they will have different weights. They'll have different masses. And that's just because helium weighs more. It has a higher mass. So since helium has a higher mass per atom, that's like saying, okay, I have a mole of cars. Cars are heavier than a mole of tires. Hydrogen is naturally lighter. It's naturally less massive, so it's going to, on the macro level, when we weigh these out, when we mass them out, it's going to have, hydrogen is going to have less mass than helium, but they would have the same exact number of atoms. Another review again. I'm going to hammer this home. So the number of atoms in a mole is always the same, and that's called Avogadro's number. And Avogadro's number is this glorious thing. And it doesn't really matter what we're talking about. We could be talking about ions, we could be talking about formula units, we could be talking about molecules. We could be talking about dogs. We could be talking about, you could have a mole of Mr. Parks's, and then life would just be the worst in the whole world. So thank goodness there's only one of me I have to put up with. But a mole is just a number. Keep that in mind, and it's Avogadro's number.
All right, so yeah, different clothes, shaved. What I'm doing is I'm redoing the slides. Some of them didn't go well, some of them you couldn't hear me. So this is me redoing them now that I actually have time. So the mole concept allows us to describe the number of particles, basically, within a given amount of substance. So this idea, 1 mole is equal to 6.02 times 10 to the 23 atoms. I'm going to just start calling this particles because it's talking about all of these things. Formula units, ions, compounds, it's talking about all of these things. So then when we set this up, it's a conversion rate, dimensional analysis. So an example of what I'm talking about is if we have, let's say, 300 centimeters, and I want to know how many meters that is. What I would be doing is we need to multiply by a conversion rate. So for every 100 centimeters, there's 1 meter, or for every 1 meter, there's 100 centimeters. The one thing I want us to get away from, because pretty much everybody always goes, so I multiply, right? And it's like, no, you divide. Why? It's because of this. You need to cancel out the old unit. So what you need to choose is the correct conversion rate. Is it going to be this or this? And if you don't know, it turns into a big unhappy time. So we're going to just do this logically, step by step. Always get the old unit to cancel. So when I'm setting up this basic problem of 300 centimeters, I'm going to multiply this by a fraction. And since I want centimeters to get out of my life, I want this to turn into meters, I know I need to put centimeters on the bottom of the fraction, because what this allows us to do is cancel out the old unit. This would be the same as if I had 2x and I wanted to just get rid of the 2, I would multiply it by 1 over 2 so that the 2 cancels out. So I want to switch centimeters to meters. And then now why this is so nice is because it lets us just put in the respective numbers. So then how many centimeters are there in a meter? Oh, I know that. There's 100 centimeters in every 1 meter. So now, just like I did before, centimeters cancels out. That's gone. Just pretend like it never even existed before. And now whatever answer I get is going to have the unit of meters, which is super handy because that's what we wanted to find out. So then I do 300 times 1 divided by 100, or 3 meters. I know you guys are probably like, duh, there's 3 meters and 300 centimeters. What I need you to understand is the logic behind dividing by 100 or multiplying by 1, because we're going to take that logic and apply it to every single one of these problems. So just like here, what you're going to get is, so here's my question. Questions are never super fun, but what I know is I want to know how many atoms are in 3 moles of aluminum. So whatever value you know, just write it down. 3 moles of aluminum. And then the way I set up these problems is like this, where you can kind of imagine this as some fraction times another fraction, and so on and so forth. Yeah, spelt it right. So every problem is going to have 2 parts to it. You're going to have a unit, which would be moles, atoms, that's an N. Moles, atoms, grams is a unit, concentration is a unit, we'll get there soon enough. And then you're also going to have a a chemical, I'm going to call it. This could be a compound, an atom, a molecule, an ion, anything. So there's my unit, and then aluminum in this situation would be my chemical. You can only ever have one of these things happening at a time. So you can change the unit, but then the chemical needs to stay the same, or you can change the chemical, but the unit needs to stay the same. And we're going to get into that more as we get deeper into the content. So since I can see the question has two different units, I'm going from moles. What's wrong with me? From moles to atoms, I'm only changing the unit. Another clue that I know that this is the case is the only element that's talked about here is aluminum. So probably not changing the chemical since there's no other chemical available. So then what I know is I don't want moles. So just like up here, I'm going to put moles on the bottom, moles of aluminum. And I want to switch it from moles to atoms. So atoms is going to be on top, and I'm still talking about aluminum. Please notice, pretty please, I'm choosing to change the unit, therefore my chemical must stay the same. Aluminum never changed within the fraction. I'm only changing the unit. And since that's the case, now that I have my fractions set up, what I can do is just take my respective numbers and put them with what they go with. So 1 mole has 6.02 times 10 to the 23rd atoms. I get to cancel out my old unit, and then just by looking at this, and if you want to, what you can imagine is I'm also canceling out aluminum since that's on the bottom of the fraction as well. But since it's also on the top here, it's going to carry over into the answer. So then my answer is going to have whatever the number is, but the unit is going to be atoms, and the chemical is going to be aluminum. So then I just do 3 times 6.02 times 10 to the 23rd divided by 1. You can just take your calculator and bang all of this in there. If it's paper 1, you can't. Paper 2, you can. Paper 1, I'll teach you how to do the mental math, but what I always imagine is I just do in my head 3 times 6, which gives me 18, times 10 to the 23rd, and then I just shift my decimal place over and increase my exponent by 1. So you should get 1.8 times 10 to the 24 atoms of aluminum. Put a box around your answer, take your pencil, throw it on the table because you just killed the problem.
Okay, so when I was first learning stoichiometry, I was taught a little trick, and it was called Mole Island. So a good way to remember that like the order in which you have to go through these problems is pretend like you have 3 different islands. And right here we've got a wonderful little ocean scene, and it's very tropical. And just because I can, I'll put a little palm tree. If you can't tell, I am not an art teacher. I teach science for a reason, because this is hideous. So anyways, in the middle you have Mole Island. And off to the left here we have atoms. And to the right we have grams. Whenever you see a problem, you need to figure out what island am I on and what island am I getting to. So for example, if I was standing here on Atom Island, and I wanted to get here. So I want grams. I have to go through Mole Island first. I have to catch the boat to Mole Island. So I have to go from atoms to moles before I could ever get to grams. So a good example, I'll just come up with a problem, is let's say we have 3.02 times 10 to the 22nd atoms. And I want to know, and I guess let's say these are atoms of hydrogen. And I want to know how many grams that is. Problem starts out the same exact way. I'm going to make my little box. And I'm going to put my given, what I know, goes up on the top. So 3.02 times 10 to the 22nd atoms of hydrogen. And I'm going to just make my first conversion. So I'm going from atoms to moles. And remember, I'm taking this unit I have here, and I'm going to just place it down below so I can cancel it out. So I've got atoms of H, and I need to switch it to moles of H. Remember that there are 6.02 times 10 to the 23rd atoms in 1 mole. And I'm going to just take those numbers and put them where they belong. So the conversion is 6.02 times 10 to the 23 for every 1 mole. That will allow me to cancel out my old unit. And now I have successfully moved from Atom Island to Mole Island. Now, I'm still not quite where I want to be. I want to make it all the way over to grams. So I know I need to do one more conversion step. I need to go over, gotta switch colors. I need to make it one more step over to grams. So I have to go from Mole Island, moles of H. I'm going to catch the boat over here, and I know this is childish, but it worked wonders for me. So let's color that in. So I'm going to catch the boat from Mole Island to Gram Island. So grams of H is going to go up here. And then remember, 1 mole is also equal to the atomic mass in grams. The atomic mass, and once again, I'll just draw this out for you. If you're looking at the box where hydrogen is, it's going to go 1, H, and then 1.01. This bottom number is your atomic mass. Hydrogen, on average, weighs 1.01 AMU. So then what I'm seeing here is for every 1 mole, and I'm getting that from the conversion factor here, 1 mole is going to equal the atomic mass in grams. Oops. That's kind of looking like an ing, so let me fix that for you. In grams. And since I know the atomic mass for hydrogen is 1.01, that is going to be the number I'm going to put up top here, 1.01. I can cancel out my old unit, moles of H divided by moles of H will both go away, and then now I can just put this in a calculator. So I would put this in as 3.02 times 10 to the 22nd times 1 times 1.01 divided by 6.02 times 10 to the 23rd times 1. As I put this in my calculator, I see that I'm going to get let me do the conversion quick. My final answer should be 0.05 .07 grams of hydrogen. I'm 99% sure that's right. I don't have a calculator with me right now, so I'm actually doing this on my phone, so I might lose track of a decimal place. If it's wrong, correct me. If you got a different number on your calculator, let me know, but I'm 90% sure that's right. When you're trying to figure out what to round to, so should I put, how far along should I move the decimal place? If I have 3 numbers to start, my answer should have 3 numbers that are not 0. We'll talk about significant figures later. I'll probably have a lesson on that Friday when I see you, just a really quick review. But that is how you're going to do these multiple step problems, to go from atoms to moles to atoms, or atoms to moles to grams. So if we were going to do a conversion of this, so if I wanted to know how much would 2.34 moles of carbon weigh, the way I want you to set it up is like this. So this goes back to the idea of dimensional analysis. I want you to just set up a little crisscross. Whatever you know, whatever value you're given, goes right here. So the given is going to go in the upper left. So I'm going to put 2.34 moles of carbon. And then remember from the dimensional analysis video, if I was going to convert, let's say, 76 meters to kilometers, I'm going to show you this example, and I'm going to come back to the stoichiometry one down here. We would set it up like this, where it would be 76 meters. I'm going to take my unit, and I'm going to drop it down. So it's going to just go right there. So I would end up with meters on the bottom, and then whatever I want to switch it to, so I want to switch it to kilometers, I'm going to put that up top. And then I'm going to write in the respective values. There are 1,000 meters in each kilometer. And now what that lets me do is I can look at my units, and I know meters divided by meters is going to cancel out. So whatever is going to come out is going to have a unit of kilometers. And then I'm going to multiply the numbers on top, so I would end up with 76 times 1 divided by 1,000. So view this as like a big fraction. So then we would end up with a final answer of 0.076 kilometers. I'm going to take that same idea and I'm going to apply it down here now. So I'm going to just take moles of carbon, and I'm going to write that on the bottom part of my grid here. So moles of carbon. And I want to know how much would it weigh. So whenever I see weigh, I need to be thinking grams. So I'm going to switch moles of carbon to grams of carbon. This is a big fraction, so this is the numerator of the fraction, and this would just be the denominator. And then I'm going to set up my relationship. I know that 12.01 grams of carbon equals 1 mole of carbon. And I'm going to just take this and put the numbers where they belong. So 1 mole is equal to 12.01. My unit will cancel out, so I no longer have moles of carbon, because moles of carbon on top and on bottom, I can cross those out, and whatever my answer is, whenever I do this number, this is going to be the new unit that I have. So our answer would come out to be something in grams of carbon. And then I'm going to just do 2.34 times 12.01 divided by 1. And I'm going to put that in my calculator. I don't know how to use a calculator. I know how to use a calculator. I don't know how to use a calculator on this program effectively yet. So you'll be seeing me do my calculations off to the side. 12.01, and I end up with an answer of 28.1 grams of carbon. Real quick and easy one-step problem. We're going to get to a point where there's going to be 3 or 4 of these steps. And I want you to see this method so that we can repeat it over and over again. And you can follow along the track and see where you're at. I'm going to erase all of this work right now just because it's covering up the next question. So then now if I have how many moles of magnesium is 24.31. So I'm going to make a little grid again. And up here I'm going to just put my given. So the given is up here. The value that I know always goes top left. So 24.31 grams of magnesium. I'm going to take that unit, and the very first thing I'm going to do is I'm going to just drop it down here so I can get it to cancel out, because I know I don't want grams of magnesium. So I'll put grams of magnesium up here, and then whatever I want to switch it to is going to go up top. So what I want to change it to, that's going to go right up here. I'm looking for how many moles, so then I'm going to just do moles of magnesium. And then I'm going to look on the periodic table to find what that relationship is. So after looking on the periodic table, I know that I have 24.31 grams of magnesium is equal to 1 mole. And then I'm going to just insert the numbers there. I can cross out my old unit because I know they're going to cancel out. Grams of magnesium divided by grams of magnesium, they go away. So then I just end up with a fraction again. So 24.31 times 1 divided by 24.31. This equals 1. And then this is the only unit I have left. It's moles of magnesium. So I know that my unit that's going to go along with this is going to be 1 mole of magnesium. If this setup that I have going on right here with this grid isn't making sense, you can do it with fractions, like a fractional setup. If you've seen it that way before, you'll get the same answer. It's just what I really want you to get into the habit of is this pattern of crossing out units that cancel. If you have a way of doing it in your mind that works perfectly for you and you know how to do the process, that's fine. I'm not going to force you to do it a way that doesn't make sense. But if it's unclear how to do this, and this is starting to make it a little bit easier, go with this. This is going to help you when we get to multi-step problems. I'm going to erase this one more time. This is going to be a little bit trickier because what we're doing is we're going from atoms. We're trying to get 2 atoms, and we're only given grams. So the way this is going to get set up is, remember, we know that the atomic mass in grams is equal to 1 mole, and that's also equal to 6.02 times 10 to the 23rd atoms. So what we're given is something in grams. So I'm going to set up my little chart. 1.00 grams of lithium. And then I'm going to switch it from grams, so from grams to moles. We can't just go straight to atoms. We have to go through moles first. Very important. Same pattern. I'm going to just take this unit that I have. I'm going to take this grams of lithium, and I'm going to place it down there. Grams of lithium. And I'm going to switch grams to moles. I'm going to look on the periodic table again to see what the value is for lithium. Lithium is 6.94, and that equals 1 mole. So then what I'll do is I'll cross out this old unit. I changed it from grams to moles. We're not done yet because we're looking for atoms. So what we're going to do then is another step farther. I immediately wish that box was bigger. That was a mistake. I'm going to take moles of lithium and put it down there, and I'm going to switch it to atoms. So now what I'll be using is this conversion factor. I know 1 mole of lithium is going to have 6.02 times 10 to the 23rd. Ugh, I know that's small. I'm sorry, that was a mistake. And then what that allows me to do is cancel out the second unit. So I changed it from grams to moles. And now that I have moles on top and moles on the bottom again, I can cancel this out one more time. So I know that my final answer is going to be in atoms, because that is the only unit I have left. Atoms is the last thing there. So now what I'm just going to do is put this in my calculator. So it's going to be, the fraction is, and I'm going to write this up here. I would have 1 times 1, sorry, 1.00, that's important, times 6.02 times 10 to the 23 divided by 6.94 times 1. So I'm hoping you're kind of seeing how this is like a big fraction again. And then we're just saving all the actual computation for last. So this is where you're basically just turning into a big calculator and punching it in. I'm going to use my calculator off to the side here. So I'm going to put this in. Move it over, and I end up with an answer of 8.67 times 10 to the 22nd. I already made my adjustment on the scientific notation. So if you, once again, if you don't understand the scientific notation part of it, let me know, and I'll clear that up for you. This is the very first time you've seen, it might be, I could be totally wrong, you've seen this before, but this is the first time that we've gone over a multiple step problem, and there are going to be ones that are going to be twice as long as this. So this, using the units to guide you in the next step and the step after that, is going to be a very useful habit in the long run. Whenever I do these, I'm going to refer back to this mole island idea. I know it's childish, but it's going to help you see how many steps that we have to do. So remember, it's over here it's going to be atoms. In the middle we have moles, that's a small one. And then on the far right we've got grams. So what I'm seeing here is I'm starting off with 3 moles, a given, so I know I'm here, and I want to know how many atoms. So I'm going to only have to do one step. I have to transfer 1 island. So then I'll set up my box. I know I have 3 moles of aluminum. I'm going to take this unit and drop it down into the lower right. Moles of aluminum. And I want to know atoms. There are same number of atoms in 1 mole, so I'm going to just take those values and place them in the appropriate box. 6.02 times 10 to the 23. For every 1 mole, I can cancel out my old unit, and I would just end up with 3 times 6.02 times 10 to the 23 divided by 1, or, it's a bad equal sign, you should end up getting 18.06 times 10 to the 23. Remember, proper scientific notation only has 1 number in front of the decimal place. So what we're going to do is we are going to shift this decimal over 1, and we're going to increase this by 1. So your correct answer should be 1.8 times 10 to the 24th. When we talk about significant figures, I'm going to come back to this problem because this answer is not technically correct. So right now this is fine in terms of math, but when we learn about significant figures, or you're going to hear me call them sig figs, you need to tell me why this is wrong. So for right now the math and the process is good, but in a bit, so on Friday probably, you'll start to learn a little bit more about why this isn't quite correct. So bring this up in class. This will be good for you. Same thing, but we're just going to go backwards. So now I know I have 3.0 times 10 to the 23 atoms of Al. That's my given. Atoms to moles is a one-step problem. And that's just because we have atoms, moles, grams. Since I'm on atoms and I want to get over here, I only need to change islands one time. Atoms, Al, got that. Take my unit, drop it down, so atoms of Al will go there. And I want to switch it to moles of aluminum, and I'm going to just take my numbers and put them in the correct corresponding spots. 6.02 times 10 to the 23, cross out my old unit, and I should end up with an answer of 0.498 moles, or if you're going to round that, it's going to be 0.50 moles of aluminum. You need to give me the full and complete unit, so keep that in mind. This one's a little bit different, same idea, except now what I have is a different unit to start. So I know I have 46.0 grams of sodium, and I want to know how many moles of sodium atoms. When you see this, the reason why this is a little bit trickier is because you're seeing the word moles and atoms, and you might get mixed up, like, oh, he wants atoms. No, I want to know how many moles. There's the key phrase, how many moles. So remember, it is atoms, moles, and over here we've got grams. Starting on grams, I need to get to moles, so it's going to be one step. I'm going to take my unit and drop it down, so grams of sodium, and I'm switching it to moles of sodium. I'm going to find the grams number on the periodic table, so remember, I'll draw it out for you again. On the periodic table, you will see the sodium representation look like this, where you have 11 and a 22.99. Remember, this is the number we want, so I'm going to put 22.99 on the bottom, and that's 1 mole of sodium. I will cancel out my old unit. This is telling me to do 46.0 times 1 divided by 22.99, or I should end up with an answer equal to 2.0. Where's my pen? There it is. Moles of sodium. Try to get in the habit of putting a box or a circle around your answer, just because it helps me find it much quicker. If you forget to do it, it's not that big of a deal. So the difference between gram molar mass and gram formula mass is just the types of bonds. So if we're trying to figure out gram molar mass of chlorine 2, I would just look on my periodic table. I see it looks like this. So I have 17 Cl and then 35.45. And so if I was doing Cl2, I would just do 2 times chlorine, because there's 2 chlorines there. 35.45, and you end up with an answer of 70.90. So that's how many grams per mole there are. So you need 70.90 grams for every 1 mole. If we were doing CH4, you would just do the carbon, which is 12.01, and then you would add the 4 hydrogens, so 4 times 1.01. So I would get 12.01 plus 4.04 equals 16.05 grams per mole. This is all right off the periodic table, so these numbers here, this number, and this number I got off the periodic table. Just like this one I did up here. It's just this bottom number, the atomic mass. The gram formula mass is just a difference if it's an ionic compound. We're going to talk more about this later. I just wanted to expose you to these ideas right now. So, but right now, just realize that we're going to be calling this molar mass. That's the key word that you need to know. So then if I had NaCl, 2 different compounds, I would just find sodium, which is 22.99, and then I would add on the chlorine, which is 35.45, and I would get an answer of 5, nope, sorry, I'm doing this one in my head, 57, 58, 58.44 grams per mole. So it's the same exact idea. When you see something like this, so I'm seeing 2 capital letters here, so I know that there are 2 different elements. That's an oxygen and a hydrogen. This is 1 calcium, because there's not a number behind it. And then this 2 distributes, just like in math, to all of the elements inside of it. So 1 calcium, 2 oxygens. You are also going to see me when I write oxygen, I don't like to just use the symbol. So if I were to use the symbol, it would look like this, 2 oxygens. That looks a lot like 20. So when I do this, you'll see me write the OXY just to avoid confusion. And then 2 hydrogens. And we do it the same exact way. So I would do 1 times calcium, because there's only 1 calcium, 40.08, plus 2 times oxygen. Oxygen is 16.00, plus 2 times 1.01, and that's just the weight of hydrogen, the mass of hydrogen. So I end up with 40.08 plus 32.00 plus 2.02, and I'm going to add them all up, and I would get an answer of 74.10 grams per mole. A good way to think about this is it's just like if you and your friend got on a scale together, what would you do with your weights? You would just add them up. Same idea. Alright, so then now let's take this idea and just put it back into the context of mole to mass. So we're going to be using this dimensional analysis just like we talked about in one of the first videos. So if I have how many grams are in 3.50 moles of CO2, whenever I see this, I'm going to start to figure out how many grams per mole is there. So I'm going to do 1 carbon. So 1 times carbon is 12.01 plus 2 oxygens. 2 times 16.00. So I end up with 12.01 plus 32.00, or that ends up being 44.01 grams per mole. So I know the molecular mass of CO2 is 44.0, let me make that a little bit more clear, 0.1. I think that just made it even worse, sorry. And then it's the same type of problem. Make your little box, and I have 3.5 moles of CO2. I'm going to take this unit and put it down here, so moles CO2, and I want to switch it to grams. I know for every 1 mole of CO2, I would need 44.01 grams. Cancel out my old unit, and put this in my calculator. So you should end up getting 154 grams of CO2. Same type of problem, it's just one little bit extra step where you got to figure out how much does the whole molecule weigh now. I'm going to erase this, the previous problem, so that I can work on this one down here. But you're going to see it's the same exact pattern. So I'm going to just find sodium and bromine. Sodium weighs, so Na weighs, has a mass of 22.99. Bromine has a mass of 79.91. Since there's only one of each of these, I can just add them up. 0, carry the 1, 9, point, carry the 1, 2, carry the 1, 102.90 grams per mole. And then it is the same exact type of problem. So you'll see 150 grams of NABR. I'm going to take my unit and lower it down there, so grams NABR. And I'm going to switch this over to moles NABR. 1, and then I'm going to take this number right there and put it in the blank. So 102.90. I will cancel out my old unit, so I'm not using grams of NABR anymore. And then now I just need to put it in a calculator. And then I end up getting an answer of 1.46 moles NABR. Make sure you give me all of this information. So tell me, what is the compound you're talking about? You have to tell me NABR, and you also have to tell me the unit that there is there too. Alright, so then some more examples. Just want to keep doing these until I know you guys fully, I hope you fully understand them. So we're just going to calculate some molar masses again. I have 2 sodium, so 2 Na, so 2 times 22.99. Remember that this number is off the periodic table. And then I have 1 sulfur, 1 times, and then sulfur is 32.06. I'm going to find these two numbers. I should end up getting 45.98 for this one and 32.06. And then add them up. This will give me 78.04 grams per mole. This is another one where I'm showing you that you have to do the distribution. So this 2 multiplies all the numbers inside here. So what I'm seeing here is 1 calcium, 2 nitrogens, because there was only 1 before, but now there's 2 of them. There were 3 oxygens here, but now there's 2 times 3 for a total of 6 oxygens. So I would do 1 times calcium is 40.08. Oops, 08. 2 nitrogen, so 2 times 14.01. 6 times 16.00, and I'm going to just get these numbers. 8.02, 40.08. 6 times 16 is 96. Yep. And then add them all up. So 0, 1, 0.417, 170.10. And then don't forget the unit, grams per mole. I think I have one more on this guy, on this slide. Do I? Yeah, alright, this is going to be more annoying, but remember this 3 distributes to everything inside the parentheses. So what I have here is 3 nitrogens, 12 hydrogens, 1 phosphorus, and then 4 oxygens. So I'm going to do 3 times 14.01, 12 times 1.01, 1 times, what is phosphorus? 30.97. And then 4 times 16.00, that is going to be 64. 30.97, this is going to be 12.12, and then this is going to be 0.03, 12, 30, 42. And then now that you have these, add them all up. I'm going to use a calculator for this one. And then after adding them all up, I get an answer of, where's my pen? There it is. 149.07 grams per mole. Same exact pattern that we've seen before. I'm going to just do a few more of these and then we're going to move on to the next subject. So then, how many moles is 4.56 grams of CO2? I'm going to just do 1 carbon, 2 oxygens, 2 times 16.00, 1 times 12.01, 12.01, 32.00, 44.01, and then I'm going to set up the problem like normal. So 4.56 grams of CO2. Take that unit, drop it down, change it to moles, and then I'm going to do 1 mole, moles of CO2. And 44.01. Cancel out my old unit, and then do 4.56 divided by 44.01 divided by 44.01. Now I get 0.104 moles of CO2. I believe I have one more on this slide, so I'm going to erase this so we can see this. And now what I want you to see is I want to know how many molecules are in 6.8 grams. So remember, Mole Island goes atoms or molecules, moles in the middle, and then grams. So right now we're here, and we need to make 2 conversions. So this one's going to be a little bit longer. Let's switch to black because the red is starting to hurt my eyes. Let's figure out what the molar mass of this is. So I've got 1 carbon, 1 times 12.01 equals 12.01. Then I've got 4 hydrogens, 4 times 1.01, 4.04, 16.05. So then I'm going to just set it all up again. So I am at 6.8 grams of CH4. This is called methane. I'm going to take that unit and drop it down. So I've got grams of CH4. And I'm going from grams to moles first. So up top will be moles. CH4. And for every 1 mole, it's going to be 16.05. I'll cancel out my old unit. I'm still not where I want to be. I'm on moles, so I need to make one more conversion into atoms or molecules. I'll take my old unit, moles, CH4. So this unit, oops, CH4. That's pretty ugly, sorry. So this guy, my moles of CH4, I just took it and dropped it to the lower right again. And I'm going to go from moles to molecules. CH4. Oof, does not look good. I apologize. I'm only making it worse. Remember Avogadro's number, so 6.02 times 10 to the 23rd is that number for atoms or molecules for every 1 mole. So then when I'm putting this into my calculator, I would do 6.8 times 6.02 times 10 to the 23rd, divide that by 16.05. So you should end up getting, let me emphasize this decimal, 6.8. You should end up getting an answer of 2.55 times 10 to the 23 molecules of CH4. So this is an example of a multiple step problem. You'll start to see these more and more as we go along. Gases. Oh, finally something new. Okay, so a lot of the chemicals that we are going to be dealing with are gases. Because of that, we have issues. So we can't touch them, and they end up being very difficult to weigh. So remember, we still need to figure out how many moles of a gas we have, but if we don't know how much they weigh, that's a big problem. It's hard to mass a gas because it's up in the air. So we end up taking into account a few different things. We need to know the volume and the pressure and temperature of the gas. So whenever you see a problem with a gas, you need to be looking out for what's the volume of it, what's the pressure, and what's the temperature. We need to try to compare them at the same temperature and pressure. So if I think about it like this, if you take a balloon and you bring it outside in the wintertime, that balloon starts to shrink up. And that's just because the temperature is lower outside than it is inside. So the volume changes as the temperature changes. As temperature goes down, the volume also is going to go down too. So what we end up doing is we come up with a standard set of conditions. What we say is standard temperature and pressure. We've decided that 273 degrees Kelvin and 1 atmosphere of pressure is our standard conditions. We call this standard temperature and pressure. Kelvin is it's probably a new type of unit for you all. Just know that if you need to convert to Kelvin from Celsius, Kelvin is equal to whatever the Celsius temperature is plus 273. So you just add on 273 and then you're going to be in Kelvin. If you ever see Fahrenheit, which you really shouldn't because Fahrenheit's a terrible, terrible measuring system. If you ever see Fahrenheit, just know that 32 degrees Fahrenheit equals 0 degrees Celsius equals 273. And then if you need it, I'll show you what the equation is to convert from Fahrenheit, but hopefully you won't ever see it. I'm not going to do that to you, and I don't think the IB would either. This is incredibly important. 1 atmosphere is the same as 101.3 kilopascals, or kPa, and that's the same as 760 millimeters of mercury, or 760 torr. You're going to be, later on, especially when we get into more gas laws, like more substantial stuff like that, we're going to be translating back and forth, because you're going to need to switch it based on what the constant is that you're given. So this is in the future. I just wanted to expose it to you now that there are multiple units for pressure. I didn't say this before, ATM, this just means atmosphere. So keep that in mind as well. 1 atmosphere is like, if we have a whole atmosphere on us like we normally do, this is just normal pressure. This is what we experience on a daily basis. We abbreviate standard temperature and pressure as STP. You can see that right there. At STP, so at normal standard conditions, a gas occupies 22.4 liters of space, and that is for 1 mole. So this is called the molar volume. You're going to see how this comes into play in a little bit here, but keep that in mind. So far we know 6.02 times 10 to the 23 atoms equals 1 mole. And then we also know 1 mole is equal to 22.4 liters of gas. And then we also know 1 mole is equal to the molecular mass, the molar mass, in grams. So the mole can give you a lot of information. It lets us switch all over the place. I'm running out of room there. I'm just making that word worse. I'm sorry. So once again, 1 mole is 22.4 liters of any gas at standard temperature and pressure. Let's stop there. Let's go one more. So for example, what is the volume of 4.59 moles of carbon dioxide gas at STP? Same type of problem. Set up your conversion chart. We know 4.59 moles of CO2. And we want to know the volume. Whenever you see that, you need to be thinking liters, or the IB will also use meters cubed or decimeters. I want you to just get used to the idea of this this conversion chart, and then we'll start to talk about the correct units of gas and how to switch between volumes later on. I want to talk with you guys about that in person. So then it's the same type of problem. I'm going to do moles of CO2. Taking that unit, I'm just dropping it down so that it cancels out. But now I want to know the volume of it. So I want to know liters of CO2. And remember, 1 mole is equal to 22.4 liters. So I'm going to do 22.4 up top for 1 mole. Cancel it out. Put that into my calculator. 4.59 times 22.4. I end up getting 102 liters of CO2. Just so you are aware, 1 liter equals 1 decimeter cubed. So those are the same thing. A meter cubed is a lot larger. So we'll talk about that one. For right now, don't worry too much about it. You'll mostly be seeing liters and decimeters. I'm going to erase this so we can do one more together. This is just opposite, so going backwards. So if I know I have 5.67 liters of O2 at STP, I want to know how many moles. I'm going to take that unit, liters of O2, and I'm going to switch it into moles of O2. 22.4 liters for every 1 mole. Cross out my old unit, and then I'm going to just do 5.67 divided by 22.4 because it's on the bottom, and I end up getting an answer of 0.253 moles of O2. So you should start to see the pattern that it's very similar to the ones that we were doing before, so there's not a whole lot of reason to get panicked. I'll tell you when it's starting to change up a little bit. I definitely want to stop here because this is getting to be very long, and I'll add on to this video later, so just remember where you stopped so that when Monday comes, when I update it over the weekend, you know where to go from. Okay, so I'm going to try to finish up this slideshow, and I'm going to try to make it quick because it's already an hour long, and that's much longer than I wanted it to be. So the ideal gas law. There's a direct connection between the number of particles, which is really just the number of moles. So when you see N, you should be thinking moles. the pressure, the volume, and the temperature. So what that connection is pressure times volume is equal to the moles times R times temperature. And R is, it's called the ideal gas law. So this is, sorry, not the ideal gas law. That's what Keevner is. This is called the universal gas constant. And it can be one of two numbers. It can be 8.31, but what you should notice, if it's 8.31, that's in kilopascal, so that's a unit of pressure. So our pressures are going to change, and with that, our R value is going to change. Stay calm. I'll talk about that more on Friday, but I just want you guys to get exposed to it right now. T is always in Kelvin. Always, always, always in Kelvin. So you have to convert Celsius to Kelvin. This is just an example. If there's negative 50 degrees Celsius, to convert that, you just add 273. The generic formula is Kelvin is equal to Celsius plus 273. So whatever your Celsius is, you just add 273 to it. So for example, down here, I have a temperature of 30 degrees Celsius, so I would do 30 plus 273, that equals K, which means 303 is my temperature in this situation. So T equals 303. Whenever I see KPA, I need to be thinking pressure. And whenever I see liters, or in this, and for us, I forgot to edit this from last year. This would be decimeters cubed, same exact thing. I need to be thinking volume. So that's a volume. I have a pressure, and I know my temperature. So I know P, B, T. I always know R. R is a constant. So because of that, I can solve for what I don't know. I don't know N. So I'm going to just rearrange the equation. N is equal to PV divided by R divided by T. Be careful with your brackets. And I'm going to do 101 times 5, and then once again, this should say decimeters cubed. Sorry about that. Divided by 8.31 times 303. And then careful with your brackets. And then I get an answer of 0.2 moles. So we're going to see this when we are trying to do stoichiometry, and it's not at standard temperature and pressure, it's not at STP. So whenever you see a set of conditions that isn't 0 degrees Celsius or 273 degrees Kelvin, and 1 atmosphere or 101.3 kPa. So I'll make this very clear when we get together on Friday when you need to be using this. We started to talk about stoichiometry. You guys have already gone through this, so I'm going to make this quick. It starts with a balanced equation, so you have to make sure the equation is balanced. So you need to balance first. Number one priority has to be balanced. And so what this is telling you is that 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. That's how you should be thinking about it, since everything we've talked about in these 3 bullet points is all related to moles. This is when that idea of mole island comes in, that the only way to go from one compound to another compound is it's through moles. So everything, Bo said it perfectly. I just convert it to moles and then I go from there. Like, that's exactly what you should be thinking. Switch it to moles and then figure it out. That's a great way to go about it. The coefficients are telling us how many moles are in each substance, not grams. That's why you switch it to moles first. 3 grams do not make only 2 grams of product. That's not okay. That violates the law of conservation of mass. What this is saying is that I turn 3 grams into 2 grams. Impossible. Doesn't work. Don't give me that. That's wrong. And it's just not going to fly. Don't do it. It's wrong. Okay? Good. So this is just a proof of that. The law of conservation of mass applies. So what I'm going to do is I'm going to just convert the reactants from moles to grams. So if I have 2 moles of hydrogen, I'm going to just take the moles and put it on the bottom. This is the first part that we've been doing with stoichiometry, and I'm going to switch it to whatever I want to up top. And I'm finding this number off the periodic table. So hydrogen is 1.01. There's 2 hydrogens, so that gives me 2.02. So then I know 2 moles of hydrogen is going to mean I need 4.04 moles, or sorry, 4.04 grams of hydrogen to start. And then I'm going to just do the same proof. So 1 mole of oxygen is going to end up giving me, and then I got this right off the periodic table again. So I have 2 oxygens, which means 2 times 16.00, which gives me 32. So that's going to give me a total of 32 grams. So the total mass of my reactants, so this is my reactants, is going to give me 36.04 grams. So what you should be thinking is on the left side of the equation, I have 36.04 grams. That's what I'm starting on. And then now I'm going to just do the same exact proof, but for the product side. So this is the mass of the product. So I've got 2 moles of H2O. This number is coming off of the periodic table, so I took my unit and I dropped it down, and I'm switching it to grams because I want to look for the mass of the product. Hydrogen is 1.01, and 2 hydrogens, 1 oxygen. So that's 16.00, 2.02 gives me 18.02. Ah, look at that, they match. Magic. And then I'm going to just multiply the top, divide by the bottom, and I end up with 36.04. I swear. Time out. Time out. I'm like 90% positive I just saw that number. Wonder where I saw that number from. Oh my goodness! The mass of the reactants is the same as the mass of the product. This is, once again, the law of conservation of mass. Can't break it. You can't break it. It's a law. If you break it, you go to science jail. Science jail is not a happy place. Science jail is where hopes and dreams go to die. So you're not going to break the law of conservation of mass. The best way to not break the law of conservation of mass is to don't do these reactions in grams, but switch them to moles first. Okay, so we're going to start to talk about chemical yield. I'm not going to waste your time with a whole lot of stoichiometry examples. We've done a bunch of practice with that so far. I'm going to leave you guys all Friday in class to ask me questions about that. Plus, we're going to be working with limiting and excess reactants, which is basically the same thing, but just twice over. So by the end of Friday, you're going to be so good at this that you're going to want to punch me the next time I bring it up, which is good. It just means I'm doing my job. So chemical yield. This is all about the amount of product made in a chemical reaction. There are 3 types of these. The first one is going to be theoretical yield. This is the amount of product that should be made. So in theory, this is what you should make. This is what you are getting from your calculations. If the world was perfect and you executed this reaction exactly how it should be, and nothing got lost to the environment, you should make this much product. Then we have actual yield. This is what you actually got. This is formed in the laboratory. This is either going to be given to you or you're going to measure it in lab. So you're going to actually do the experiment and get an actual yield. I'm trying to make this as clear as possible. So in theory, you should get a theoretical yield, but you will actually get a different yield, and that's fine, because that's not it. The two will never match up unless you are some sort of chemistry deity, in which case, teach me your ways. The third type is a percentage yield. This is a percentage between the actual yield and the theoretical yield, and we have a really easy chemical formula, or not chemical. We have a real easy formula for this. It's just actual yield divided by theoretical yield times 100. So your actual yield should always be less. Your theoretical yield should always be more. And so then when you multiply it by 100, you're going to get a percentage that should be less than 100%. If it's ever over 100%, that means one of two things. It means you messed up the calculations on your theoretical yield and you got a number smaller than what you should. Or when you did the experiment in your actual yield, it's still got some water in it and it's going to weigh more than it actually should. Meaning it's kind of like if you put a towel on a scale. If you put a towel on a scale when it's dry, it's not going to weigh that much. But if you put a towel on a scale when it's wet, it's going to weigh a lot more. The towel doesn't weigh more, it's just that it has some water. So that's going to come into play as well. So just keep that in mind for the future when you're writing up your conclusions for your labs, that if you end up with a percentage yield over 100%, that's one of the two reasons why. The percentage yield just tells us how efficient a reaction is, basically how good of a job did we do. The closer to 100%, the better, normally, unless you messed up your math. But we'll figure that out when that happens. It should not be bigger than 100%. If it is bigger than 100%, it's one of the two errors that I talked about. Okay, so an example problem. These are actually really easy. So according to your calculations, the theoretical yield for the production of NaCl, this is table salt, this is what you put on your food, is 13.6 grams, but your actual yield is 11.8. So you would just do 11.8 divided by 13.6 times 100. It's that easy. And you're going to see it right here. The answer would be 86.7%. That's a pretty good yield. When we start to do organic chemistry when in the laboratory in companies aim for about 50% yield, which sounds crazy that only 50% of the time the company is able to achieve what they want. That's the nature of chemistry. We're working with atoms. We're trying to manipulate things we can't see. It's still pretty hard. Like we know we have a good idea of what we're doing, but it's not perfect, but we're still trying our best. Calculating percent composition of a compound. This is going to be a little bit tricky. So like all percentages, it's going to be part divided by a whole times 100. This is every percentage you've ever seen follows this rule. So what you're going to have to do is figure out the mass of each part and then divide by the total mass. This sounds a little tricky right now, but when you start to see it in practice, it's not all that. Okay, so now we're going to start talking about calculating a percent composition, and we're going to do an example problem now. So we're going to find the mass percent for all of the elements. Notice there are 5 different elements. We have sodium, hydrogen, carbon, and then oxygen. I don't know why I put a C there instead of drawing an arrow. Don't question me. I'm the teacher. So then, just a heads up, sodium bicarbonate, this is baking soda. If you ever have heartburn, throw some baking soda in a glass and then drink it, well, with some water, and then drink it. It'll solve your heartburn immediately. Like, it's the chemistry behind it. And trust me, this is how I solve my issues. So remember, we have part divided by a whole times 100. So the whole in this case is going to be the molecular mass of sodium bicarbonate. So I'm going to just do sodium plus hydrogen plus carbon plus oxygen plus oxygen plus oxygen. Just forgot my O. One last time. And these are all numbers off the periodic table. So I end up with, so after looking at the periodic table, we're looking at average atomic mass. So I'm seeing sodium is 22.99 plus 1.01 plus 12.01 plus 16.00 plus 16.00 plus 16.00. So the whole of this is going to weigh. So I end up getting a value of the whole thing weighing 80 84.01. And now we want to figure out the mass percentage for every element. You're going to start to see a pattern here. So the mass percent, so the percent of sodium is equal to the part, so the value of sodium, 22.99, divided by the whole thing, 84.01 times 100. So the percentage of sodium ends up being 9 divided by 84.01 times 100, 84.1 is 27.37%. If I was going to do the percent mass of oxygen, let's say, I would add up all the parts, so 16 plus 16 plus 16, which is 48, and divide by the whole, 84.01 times 100. So I get 57.14%. And then this pattern continues the whole way through. Repeat, repeat, repeat. You would just need to do hydrogen and carbon next. I'm not going to do it because I'm running out of space, but it's the same exact thing. Empirical formula. This is the lowest whole number ratio of elements in a compound. You should be thinking when you see a compound, what's the common factor I can divide them all by? So we have a molecular formula, which is the actual ratio of elements in a compound. So for example, if I was looking at hydrogen peroxide, H2O2, this would be the molecular formula. But since I can divide both of these by 2, the empirical formula would just be HO. So the two can be the same, but not always. So CH2 is an empirical formula, but C2H4 is a molecular formula. CH2 doesn't exist in nature, but C2H4 is ethene, and that is an incredibly important compound for us. C3H6 is a molecular formula because both of these I can divide by 2. I can divide them by the same number. This one I can divide by, that's supposed to be a 3. I don't know why I made it a 6. So you can start to see the pattern there. H2O is both empirical and molecular. So H2O exists in the world, and I can't divide it by a whole number. So I could divide it by 1, but that doesn't really count. So I can't divide it by a number greater than 1. I can't simplify it more. So if we're looking at calculating the empirical formula, we're just trying to find the lowest whole number ratio. So basically, what can I divide all of these by? I can divide all of them by 6 in this situation. So the empirical formula would be CH2O. This is a carbohydrate by nature. Carbo, carbon, hydrate, water. The second you get this, it's going to make your life easier at the very end of next year when we start to study biochemistry. Carbohydrate. Start to think about chemistry names as nothing complex, but rather two things slammed together. Scientists are not creative at all. We just put two words and put them together. So, for example, the thing in outer space that sucks everything into it, but we can't see. We called it a black, we can't see it, hole. Everything gets sucked into it. A black hole. We're not creative people. Scientists just throw the two most obvious terms that we can think of together and we call it fancy. We're not smart. We're lazy. We are lazy individuals, and that's good for us. And then, so if we're looking at CH4N, since I can't divide these by a common number greater than 1, this is actually already the empirical formula. So this is an empirical formula to start. Empirical already. So another thing that I want to talk about, it's not just the ratio of atoms, but it's also the ratio of moles of atoms. So for example, in 1 mole of carbon dioxide, there's a mole of carbon and 2 moles of oxygen. It's kind of like if I have a dozen humans, 12 humans, there are 12 heads, but also 24 arms and 24 legs. So I can talk about the whole, and then I can also talk about the parts that make them up. In 1 molecule of CO2, there's 1 atom of carbon and 2 atoms of oxygen. Same idea. So I can split the one thing up into its 2 parts. The way we actually calculate empirical formula is going to be from a ratio of percent composition. This is going to make your life so easy. Assume you have 100 grams. So when you're looking at a percentage of composition, the percentage just kind of goes away and it just turns into grams. Then you're just going to convert the grams into moles, and then you're going to find the lowest whole number ratio. And you're going to see what this all means on the next slide. So for example, crack my neck, sorry. Calculate the empirical formula of a compound composed of 38.6% carbon, 16.22% hydrogen, and 45.11% nitrogen. This already sounds miserable. But if you assume that everything's out of 100 grams, so what you can do is, we assume that there is 38.67 grams of carbon. So we just turn the percentage sign into the gram sign. And then I'm going to just switch it over to moles. This is off the periodic table, so I know I have 3.22 moles of carbon. And I'm going to do the same exact thing with the other 2 elements. 16.22 grams of hydrogen. I just switched the percentage to a gram sign, and I divide it by the number off the periodic table. And then lastly, 45.11 grams of nitrogen, and I'm going to switch it over to moles. And then now we're going to divide everything. We're going to divide all, one too many 8s there, all by the lowest number. So in this situation, 3.219 is the lowest number that I have. So I'm going to divide all of these by 3.219. Got my 1. And then this will help you solve it out. So then, for example, for every 1 mole of carbon, I have 1 mole of nitrogen. And then for every 1 mole of nitrogen, I have 5 moles of hydrogen. So I know my empirical formula is going to be 1 carbon, 5 hydrogens, 1 nitrogen. We can do the same exact thing with this. So we can say 49.48 grams of carbon, 5.15 grams of hydrogen, 28.87 grams of nitrogen, and 16.49 grams of oxygen. And we can solve for its empirical formula. I'm going to let you do this one on your own. So now we're going to use that same exact example we used before, but we're going to work through it on this one. So remember, percentages can switch to grams just because we're pretending like we have 100 grams of this. So I'm going to do 49.48 grams of carbon, and I'm going to divide that by the molar mass, so 12.01 grams of carbon for every 1 mole. So this is going to tell me the moles of carbon. Put that in my handy dandy calculator, 49.48 divided by 12.01, and I get 4.12. I'm going to do the same thing with hydrogen. So I'm going to do that off to this side. 5.15 grams of hydrogen divided by 1.01 grams. And then I end up with 5.10, basically 5.10 moles of hydrogen. Let's go to the nitrogen. So I have 28.87 divided by the periodic table is telling me 1401 grams of nitrogen. So I know that I have 28.87 divided by 14.01, 2.06 moles of nitrogen. And the last one, 16.49 divided by, and then on the periodic table it's telling me that for grams of oxygen. 16.49 divided by 16 is 1.03 moles of O2. So now what we're going to do, I'm going to switch colors for this. I'm going to divide all of these by the smallest value we have. And the smallest value is 1.03. And this is going to give us our empirical ratio. So for carbon, I get an answer of, we have 4 moles of carbon. For nitrogen, I get an answer of 2 moles of nitrogen. For hydrogen, I get an answer of basically 5 moles of hydrogen and then 1 mole of oxygen. So I should end up with C4N2H5O. That is our empirical formula for caffeine. The next slide is going to start to help us dig deeper into it. So since we know the empirical formula is the lowest ratio, the actual molecule would weigh more. Because remember, the empirical is when we've divided it all down. So what we would do is we would divide the actual molar mass by the empirical formula mass. So if caffeine has a molar mass of 194, what is its molecular formula? Remember, this was what we came up with. It's written a little bit differently. And then this is just the molar mass found on the periodic table. Periodic table. But they're telling us it has a molar mass of 194. So we would do I got that backwards. No, that was right. 194 divided by 97.11. We should end up getting an answer of about 2. So what this is saying is this. We should do 2 times our empirical formula. So our empirical formula is only half of what the true molecular formula is. So then we would double everything up to that. This is one of the finer details of chemistry. I am not expecting us to get this until after challenge week. That's when I'm really going to start to hammer it home. So I'm looking to have this test sometime after the week after we get back from challenge week. So it's going to go challenge week. The week we get back from challenge week, it's going to be a lab, some practice time, just working with everything, and then the test the week after we get back. The week after we get back from after we get back. In 3 weeks from now. I told you guys I'm bad at counting. So then this is just another compound, another example. I'm going to let you guys try this one out on your own. If you all want to ask me questions on it, class, I would be more than happy to help you walk through this. But use the notes from before. The last 3 slides should give you all the pertinent information that you need to complete this. And then just let me know, what do you think the molecular formula is of this compound? I will see you all very soon. Have a nice day.